Here we go. Okay, well, we're up to an N of 3 here. Why don't I go ahead and start out? Today, what I was going to do is spend some time talking about using simulations based upon the model-based meta-analysis models. And the notion here is we're using these simulations as the means for doing inferences based upon the models. So we're going to talk both about, I guess, conceptually as well as nuts and bolts, although I think bulk of today will be kind of nuts and bolts around doing the simulations and talking about sort of different permutations around those. Uh, and you should have gotten a couple of emails where I indicated I've posted a couple of things. Sorry it wasn't until today, but uh, there are a couple of things that you'll see posted on the course. So, for example, I've got there's a revised set of course slides. The only part of the slides that are new is there's a little section I have there describing one of the examples that I just posted. It's actually borrowed very heavily from the MI250 course. That's our basic Bayesian analysis course. So if you've taken that recently, so that's going to be looking somewhat familiar. So we'll be using that. The two examples. One is one that you already had in the original distribution, but I made a change to it, and the only part that's really changed is I incorporated a component in there to be able to do some parallel computing to do the simulations. Otherwise, the example is what it was before. And then this other example that I called Factor 10A Sim, which is simulating from a typical population PKPD model and illustrating some of the concepts we'll talk about today. Okay, so let's get rolling. Okay, so first of all, let me make a distinction between the kinds of simulations I'm going to be talking about today and other types of simulations that you might commonly employ, such as clinical trial simulations. Though there's a lot of commonalities, what we're doing here will be slightly different than a typical trial simulation. So I'm going to be using the term population simulation to refer to simulation of what I term here a population estimand. Things like a population mean or a population percentile, maybe the probability of an event. So these are all quantities which are you can think of as being defined in probabilistic terms. And the notion here is we're trying to simulate some underlying, for lack of a better term, underlying true estimand here, a true mean or percentile and so on, given what we've learned via our modeling. So that's what we're attempting to simulate. Of course, we're not going to simulate a point estimate of these. We're going to simulate a probability distribution that's basically is a statement about our state of knowledge in that particular population estimand. And as I say, I'm trying to contrast that where we're simulating clinical trial results or individual observations. And so the idea will then to be using those simulations to characterize the probable range for some population estimand for each treatment of interest. And by probable range, I mean using things like credible intervals as a basis for saying the probable range. We can also, in some cases, take advantage of the simulations to make fairly direct probabilistic statements about things like, what's the probability that, drug A at, 10 milligrams results in a greater effect than drug B at some particular dose. So we can make probabilistic inferences like that using these simulations. And another way to think about this when we talk about trying to simulate a population estimand is what we're really talking about is we want to simulate an outcome in a way that at least theoretically is eliminating sampling variability that results from simulating a finite sample. So you can think of this as, attempting to get the result that you would expect from a conceptually infinite number of simulated values to get a population mean or whatever estimand here. Of course, we're going to be simulating a finite number, but ideally you'd like to simulate a large enough amount that when you say take a mean of all those simulated outcomes that it approaches the population mean. Okay, so let's see, what was I doing with this slide? I forget. Oh, okay. Yeah, the point here I'm going to make is first we're going to start out by talking about simulations based on models that were constructed by analyzing only summary or aggregate data, like we've been doing so far, like analyzing things like sample means, for example. And so I have some comments on that. One is that models based upon analysis of such summary statistics alone are generally not ideally suited for simulation of individual patient data, largely because the model is not going to be a complete reflection of that individual data. And if you're going to try and use such a model to do that, you're going to have to make some pretty strong assumptions about the model, in particular about the probability distributions within it, and the extent to which they do reflect the underlying, say, inter-individual variability, for example. But having said that, that doesn't mean that we can't do something with the models. We can use those models for certain categories of simulations. In particular, they're appropriate for simulating the summary statistic on which they're based, and for a population estimand for which that summary statistic is an estimator. So for example, a sample mean is going to be an estimator for a population mean. And similarly, the fraction of patients that experience some particular outcome or particular event is an estimator of the probability of that outcome. So generally, we construct our models in such a way that something like an expected value or some other parameterization would be a reflection of some underlying population mean. And we can use our analysis of these summary statistics to try and inform us about those particular estimands. So let's take an example. Let's start out, let's suppose we've got a model that takes on the following form, and this is comparable to some that we've used in our examples. So suppose this model describes the sample mean for some clinical measurement in the ICE treatment arm of some trial. So here we've got our Y bar I then represents our sample mean for that ICE treatment arm, and we've got that described in terms of a likelihood describing the residual variation here. So it's normal with some mean mu and some variance here, sigma squared over n. And then our model of the effect of that particular drug and dose is captured in terms of this mu I being some function of dose and the drug and some other parameters that we're estimating in our modeling problem. So we've got a case here then where this mu sub I for this example then would be our population mean for the effect of that ICE treatment. Now for our example, we're going to assume that there's no intertrial variation in the model parameters. We'll discuss the consequence of incorporating intertrial variation afterwards, but let's start out with the simpler case without it. So as I say, for this case, the population mean response to our dose I and drug I then is just going to be our mu I, as I said. And then once we have a set of MCMC generated posterior samples, or for that matter, posterior samples generated by any strategy, but in our case, we're using MCMC. So we've got our MCMC generated posterior samples of our parameters, theta. Given those, we can generate posterior predictions for our population mean mu for the dose of any drug in our particular model. And then we can use those simulated predictions then, and we can use the percentiles of the predictions in particular to get estimates of things like the median based on the 50th percentile or the 90% credible interval using the 5th and 95th percentiles from the distribution of those values. And that whole notion is what we'd be using repeatedly in order to do inferences based upon posterior samples. So the general notion here is that we're going to be doing simulations where we're going to sample from our posterior distribution of parameters, and for each such sample, we're going to construct an estimate of our population mean, and we're going to do that over and over and over again using different samples from the posterior distribution, so that the end result then is we'll have a distribution of values for our population mean, and from that we can do our inferences. Now for our case, again, we're working where we've already got a bunch of samples generated via WinBUGS in here. So we've got our MCMC samples, and it's from those that we're going to do this. In principle, the same concept applies if instead of having those samples already generated, if you have some other measure that you consider a posterior or pseudo-posterior, whatever we want to call it, that might be in a parametric form for those parameters. That, for example, is commonly done using things like the variance-covariance matrix for your parameter estimates out of non-mem. Sometimes people will use that as sort of a pseudo-posterior to characterize the uncertainty in the model parameters. Okay, so here I show that example in terms of a normal distribution, but the concept extends beyond that. It's readily generalized to distributions other than normal. It's most easily applied when the expected value for that distribution is some analytic function of the parameters, but it doesn't have to be. In the end, you can always come up with that expectation by just simulating multiple cases and taking a mean. So let's take that notion then and do an example. And the example I'm going to do is going to be using the stat and gem Kabine stuff that we've already done in the past. Excuse me. So we're going to do some simulations to assess the dose response of those gemcitabine statin combinations relative to marketed treatments, particularly statin ezetimibe combinations. And actually what we're going to do, if you recall back in the publication that particular example was based upon, it's just such simulations that were used to describe uh, was used to compare the treatments and support the decisions that they had done. So we're basically going to do that exercise ourselves. So again, the example is going to use the MCMC samples that were generated in the statin gemcitabine modeling examples I've shown you before. So these are going to be looking at the distribution of population mean LDL percent change from baseline values, and we're going to use simulations to predict that those population means for various doses of statins, ezetimibe, gemcitabine, and combinations of the statins and the non-statins. And the notion here is, or the objective here would be to use those simulations to assess the benefit of gemcitabine add-on therapy relative to ezetimibe statin combinations. I think that's the last. Oh, okay. Give some specifications for this. So that's the basic concept. Now this is starting to get into some of the mechanics. So what I'm going to do here is just generate a bunch of simulated population means, and we're going to do that for a range of statin doses, and I cite the specific statin doses that we'll use. So you can see it's like 0, 1, 2, 3, 4, and then it goes by fives up to 80 milligrams here. The ezetimibe doses, you can see a listing of doses here going up to 40 milligrams per day, and another sequence here of gemcitabine doses going up to 900 milligrams every 50 here, just to be able to generate relatively smooth dose response curves. For our example, I'm going to do 1,000 samples per dose combination. That's depending upon how precise you want to be about any probabilistic inferences here. That might not be enough. You'd have to look at the specific case. In fact, you could fairly easily calculate a standard error for the means when you could do the exercise, and once you do, not only can you look at the means you get, you could calculate a standard error on those to get some idea of how much precision you've got and whether or not you may need to do somewhat more samples in order to have adequate precision. But for now, we'll just pick a nice round number of 1,000. And we're going to create some plots that'll show posterior median and 90% credible intervals for our population mean LDL percent change from baseline, mainly showing them versus dose. We'll do that for statin monotherapy, non-statin monotherapy, and then we'll do a couple specific cases where we combine atorvastatin with ezetimibe 10 milligrams per day and compare that to atorvastatin with and without gemcitabine 900 milligrams per day. The rationale meaning those were they're kind of the upper end of their dose range, actually it's not really upper ends ezetimibe. Why don't we just call it these are the likely labeled doses for these. Let's see. Okay, so let's go ahead and do the example. You got the premise. Again, I'm not going to try and build this from scratch right here, but bring out some of the key elements. So this is in the statin gemcitabine sim. As I say, if you haven't downloaded the stuff from the website yet, don't worry about it, because the differences between this script and the one that you already have from the original distribution is fairly minor. Go ahead and fire that up. Oops, I just scrolled the wrong thing there. There we go. Actually, let me get that back down to where we want it. We may want to revisit that. Okay. So I'm going to take advantage of the fact we've already done the MCMC samples. In fact, let's go back to the files. What I'm going to be doing is we did the statin gem Kabine. In particular, I'm going to use the statin gem Kabine trunk Emax. Oops, I just did something I didn't want to do. Okay, let's get back to that. Okay, we're going to use the statin gem Kabine trunk Emax, and rather than rerun the WinBUGs, what I'll do is we're going to grab the file I'm highlighting right there, the what ends that ends in .fit.r save. Okay, so what that contains is just a sort of a binary formatted version of the bugs.fit object that was generated when we ran the example before. So I'm just going to pull that in to reconstitute the bugs fit object. And that's where we're going to get our MCMC samples in order to do our simulations. So some of the first bits are just bookkeeping. I'm basically telling it this is the model I want, the statin gem Kabine trunk Emax, and I'll use that to construct the necessary paths to find that particular file. And the example name here just corresponds to the name of the folder containing this script. The next bit is part of something that I added from the original thing to incorporate some parallel processing in here. And as I mentioned in my email, I won't swear that this will run on Windows. I haven't tried running it. I chose an approach which in theory ought to port to Windows, but I haven't tested it. So if anybody wants to take a shot at it, please let me know how it worked out. But because in case you haven't figured it out, I'm doing this work on a Macintosh here. But the idea is that when we're doing the kinds of simulations we're talking about now, is unlike MCMC, where you're doing a sequence of simulations which are correlated with each other and which depend upon the previous simulated result. Here we're doing a bunch of independent simulations, so we can throw those out to however many processes we have handy. And the way I set this one up is it's set up to take advantage of however many cores you've got on the particular machine you're running it on. The approach would be generalizable to multiple machines too, but the way I've written it here is it'll only work on the cores in your own. And and even I think at this point, pretty much everybody's machines have multiple cores to some degree. The one I'm on, for example, is just your typical MacBook Pro, which has got 8 cores in it. So we can take advantage of that rather than the default, which R uses, which is only to run on 1 core at a time. Okay, enough about that. The next stuff is a bunch of bookkeeping again to set paths and pull in some code. I'll just mention this. I think the version I distributed had this uncommented. You'll want to comment out this line because that actually points to the path on my machine as opposed to your flash drive. Pulling in a few, well, we're setting the working directory, pulling in a few other things here. The one line which is different from before is I've got this call to the parallel library, which now, since I think R version 2.14, I believe, is distributed as part of the R package. Okay. The next things I've got here is I've declared some functions here to help us with the simulations. And I got a reminder, did I only do one? Oh, I'm thinking of another example here. Yeah, for this one, it's just one. So what I'm setting up for here is a function that will calculate a population mean given a single set of parameters. And basically that means is given one row from our matrix containing our posterior samples, it's going to generate a population mean corresponding to, actually it's going to do that for each row of a design matrix, or actually I think I set it up as, did I do as a matrix or data frame? Now I got to remind myself, a data frame. Okay, so what you're going to pass in here is P is just a vector, which is contains our model parameters. And the way we're going to get that is actually by pulling out a row from our posterior matrix. Design is a data frame that's going to describe our various independent variable values. So you can see that here. So in particular, it's going to contain, well, this is kind of a general statement, dose, drug, and any other covariates needed by the model. In this particular case, I believe it is only dose, and we'll see when I construct it down below, but I believe it's only dose and drug in this instance. But you can do that for however many. Actually, I should be careful. It's drug 1, drug 2, dose 1, dose 2, corresponding to the statin and non-statins. So it allows for us to have combinations. Let's see. We'll talk more about this when we get later on, when I talk about incorporating intertrial variation here, on whether we actually want to pull intertrial simulation into the simulations, and if so, how. For now, let's ignore that, and we'll touch on that later. So ignore the if intertrial component in here. I tell you the truth, I'm trying to remember why I had that particular statement in there. Oh, that's right. I forgot. The non-statin one is the Ezetimibe, and we assumed that the N value for that was 1. I forgot about that. So all that's going on in here, in fact, I won't even go through this in detail. All that's going on in here is this is just calculating our LDL, or as I put it here, LDL hat, which is our LDL percent change from baseline, the mean for our population mean based on this. Now, in this particular case, recall that for our model, this is similar to, where do we go, the situation here. We've got a model which described the population mean change as a combination. We remember it was a couple of Emax models, an Emax model for or sigmoid Emax model for statin effect, another such model for non-statin, and then a combination effect. But that would predict that mean percent change. So that, and it just used a simple normal distribution for the residual variation here. Well, we don't even need to simulate from the normal distribution because the mu is already an estimate, or a prediction, if you like, of the population mean. So we'll just use that directly. And that's all that's going on here. You get your final thing here. So you got your LDL hat, equals the placebo effect minus the statin effect minus the non-statin effect, and plus that interaction term in here. So that's going to generate that. So it's going to generate one value of the mean for each possible combination of variables in the design, in this design data frame here. Now that's only going to take, and what we're going to do then is take this and run it once for well, I can't remember if I'm doing each row or doing a sample of rows, but so it's going to be called several times, corresponding to different rows taken from the posterior matrix. Some of this again is bookkeeping. This is just going to be used to subset the portion of that bugs fit object to only contain the parameters of interest. It's a rather large matrix containing a bunch of other predictions in that we're not interested in, so it'll cull those out. So this statement is just pulling in that bugs fit object. This is just reorganizing it into a simple matrix. That's probably overcomplicated now that I think of it, because the bugs fit object actually contains such a matrix, but that's beside the point. So we're going to get a matrix, and it's subsetting only the parameters that were in that parameters to plot list there. Now it's going to go down and construct the design matrix that we're interested in, as well as a few other things. So this is just reminding us of the coding we use, the numerical codes we use to represent the different statins and non-statins. NSIM is going to be the number of posterior samples we're going to make use of to do our to get our distribution of population means. So this is just specifying that list of statin doses and Ezetimibe doses and Kabine doses, and then using those to construct our design matrix consisting of the different combinations here. So here it's just constructing, you can see here it's going to construct the different combinations of statins. Well, here you've got the different statins you have, and we're using the same range of doses for all the statins in this instance. So, and by the way, if you've never used expand grid before, it's basically taking a group of vectors here. So you've got a vector drug 1, dose 1, drug 2, dose 2, and it's generating all possible combinations of those, of the values of those vectors. It's doing the same thing. Well, it does the first thing for Ezetimibe, it does the same thing for Kabine, and then it uses the R-bind to pull them all together. So we get all the combinations we're interested in. One comment I make here is I'm being a little bit sloppy here, because this actually results in some redundant arms. In particular, we're probably getting more than one. Let's see, we're getting some redundant placebo arms, for instance, out of this that I probably ought to call out, but I was lazy and I didn't do that. Okay, and then the next part is where the business end of the simulation is. The original code you got would have only had this line, which does the job. It just uses the apply statement to go down the rows of the posterior matrix. So remind you, the posterior matrix is nothing more than a, you know what, let's actually, rather than try to describe it, maybe it's better to show it. Okay, let's enlarge that a bit. Let's actually go ahead and run the first part of this just to pull everything in, make sure I didn't do anything dumb and make any mistakes here. Okay, we'll pull all of that in. Okay, let's take it down just short of where we do the simulations themselves. Okay, let's make this a little wider. Sure, I don't see any error messages, so I think we're okay. Okay, what I wanted to show you was just the structure of the posterior matrix, if you haven't already looked at that in previous runs. It's going to stretch it out for a while, but you get the general gist here. So here I just looked at the first few rows. So you can see the column headers here correspond to all the parameters that we have in our model. So like your E0 mean, the Emax for the statins, the exponent for the statins, and here our that was the intertrial variation, which we're actually not going to make use of right now, nor are we going to make use of the sigma, which is our standard deviation for the residual variation. But then you got, and it's got some here like our reparameterization E star, and then we have our ED50s for all the different statins, and so on. So that's the structure we're working with. And each row in here corresponds to a sample from, as a single MCMC simulated set of values, and thus constitutes our estimate of a sample from a posterior distribution here. So each one of these is what we would grab and pass into our function when we simulate it. So here, when I use the apply, I'm going to construct, first of all, let's see, I got overly complicated here. Okay, all this gibberish off to the inside the brackets here is just to generate a random sample from the list of rows from our posterior matrix. And if the number of simulations is less than the number of rows, it does so without replacement. If it goes above that, it does it with replacement. So that's just a little. So, but the core thing is this is a matrix, the rows of which we want a sample from, and by using a 1 here, it's going to be sampling from rows as opposed to columns. And then it runs that function we just described. And then I'm also passing the various components here. Actually, let's say intertrial equals false for now. As I say, more about that later. Okay, so that would run that. That pred then would then be a matrix coming out here containing all of the distributions we're interested in. Now, the bit above that is basically the same function except set up to do it in a multi-processing environment, to basically send things out to multiple cores. And if you haven't used the parallel package yet, this is one way you can do it. Actually, on a Macintosh, it can be done even simpler than this. I can actually just specify one thing here, but on Windows, I know you have to actually open the cluster and so on. So that's why I attempted to make this portable anyway. So all this is doing here is this opens up a cluster with a number of cores equal to what this thing is capable of detecting. For example, if I actually run that detect core thing, if this works, make sure that does what I think. Go down to the bottom, and you can see it produces 8. So it's telling me I've got 8 cores available here to work with. So the first statement basically opens up. In this case, it'll start up 8 R processes. The next thing here basically fires up a parallel random number generator setup in here, so that I'll have independent random numbers generated across all of the cores. And then the next statement here is almost identical to the one we already looked at, except it uses this par apply instead of apply. So it's going to fire things up across the cluster. Oh, the other part is there's an argument here telling it, basically passing in the cluster information. So that's all there is to it. Why don't we actually, this one doesn't take too long to run here. So just to illustrate, let me, wrong button. Okay, where is that? Ah, there it is. Just to give you some idea what goes on when we actually use it. Down here is a little graph for CPU usage in here, and you can see a fairly low level at the moment because we're not doing that much. If I fire up this stuff here, for instance, when I fire up the first thing here, well, just to show you, let's put this in alphabetical order. Notice right now there's only one R process going on. When I execute that command, you see all of a sudden it pops out, and you'll see 8 more got created. Should be 8 more. Yeah, there are. So there's actually now 9 processes, basically a master process plus 8 slaves which is where it's going to run the code. And then if I run, well, you don't see anything if I run the next one, so I'll just run the whole thing. If you look, and this one doesn't take very long, so don't close your eyes, don't blink, because what you'll see is briefly this will basically go to nearly 100%, meaning 100% of all 8 processors fires. At least I think it will. Let's see. Unless, of course, I made a mistake. Yeah, there they go. So anyway, it doesn't last long in this case because it's not that tough a problem. So just to illustrate that it's fairly easy to do that in R these days if you haven't already dealt with that. Okay, enough of that. I'm afraid that might be old news to many of you. So we've run that. So pred here, I forget how big, I forget which way the dimensions went on that. Okay, yeah, we don't want to look at the head on that. So, we basically got 1,000. So the number of in this case, the columns correspond to the different simulations, and the rows to the different elements of our design matrix. In fact, make sure that's right here. Do we really have that many in there? Oh, not if I don't spell it right. Yeah. So we've made there that many different combinations that we did the simulations for in here. Okay, so we went ahead and ran this. That works. So let's go ahead and make some pictures. Actually, I think they're already made. In fact, I know they're, well, we can go ahead and finish running it because I used a different name anyway. So it doesn't take that long. Okay, so I didn't do any boo-boos here. Let's take a look. So that's right here. I just did 4 pictures in this instance to illustrate this. Okay. First part of it is just aesthetics here. So this is just looking at the statin monotherapies here, just looking at dose response. So you can see that going across atorvastatin, lovastatin, and so on. These are 90% credible intervals going, and around the red, which is the estimate of our posterior median population mean LDL percent change from baseline. I think the next one is next one is the same thing, just done as shading instead. Here's our Ezetimibe and Gemkabine monotherapies. Again, this is consistent with what we had seen when we look back on that original paper where we've got the Ezetimibe you can see, drops and ends up fairly flat after you get around 10 milligrams per day. You end up with Gemkabine at higher doses. Actually, the monotherapy results in greater LDL percent changes. But when we look at it as add-on therapy, we see what was seen as an unfortunate pattern then for Gemkabine. Here with Ezetimibe, we have our predicted results are such that we end up with a fairly constant increment due to Ezetimibe when you add on. Oh, I guess I need to tell you, top curve here is atorvastatin monotherapy. So we're looking at the atorvastatin dose response by itself. And the lower curve is atorvastatin dose response with 10 milligrams per day of Ezetimibe added. Right-hand plot is the same sort of story, but now the red curve is where we have 900 milligrams per day of Gemkabine added. So again, the pattern is we see a pretty constant increment. So regardless of the dose of atorvastatin, you get an incremental benefit from Ezetimibe. That's not really the case in the case of Gemkabine, or at least the incremental benefit goes down to the point where at higher doses of of a statin, the incremental benefit is rather small. So the basic conclusion is that, all else being equal, ezetimibe would be the superior add-on therapy. Okay. So is there anything else I wanted to tell you about that particular example? Probably not right now, although I realized as I was preparing for the class, there's something I probably ought to show you. I'm not going to try and do it on the fly, but what we looked at as we're looking at, come on, where'd it go? As we're looking at this example, one can imagine you might want to be more formal about some of the inferences here, and you might want to speak in probabilistic terms about, maybe what's, for example, what's the probability that, let's say that that LDL percent change as a result of, say, something like if you gave, say, 40 milligrams of atorvastatin plus 900 of gemcitabine, what's the probability that the resulting LDL percent change is greater than or equal to that for some particular combination of atorvastatin plus ezetimibe, and actually express that in probabilistic terms. And I did not do that. And often it is a good idea to tabulate that kind of information in order to make formal assessments about things. Depending on where you are in development, you might want to do such an assessment to either decide on what dose to select for a given problem, or maybe even to decide whether or not to consider curtailing development of a particular drug. So I'm going to make a little note to myself here that I should illustrate the process of doing that. It's actually fairly straightforward. So let me just put a note to myself on that. Okay. Okay, before I move on to some variations around this simulation topic, let me see if there's any questions on what we've covered so far. Okay, nothing popping up so far. Let me take, before I talk about the next topic, let me go ahead and mention what the exercise will be, looking forward to our next lab session and proposing a hands-on exercise for you. Let's see, it's actually towards the end of what I was going to do today. Where'd we go? Too far. Actually, why don't I do it this way? There we go. Excuse me. Okay, so the exercise for this week will be to use the MCMC samples that were generated back in hands-on problem 3, and whether you use problem 3 or 3B, it doesn't make a difference. Either would be appropriate. and use those results to simulate the posterior distribution of population mean LDL percent change from baseline predicted result from various doses of atorvastatin and rosuvastatin. Of course, the idea here would be to compare the dose response of the two statins. You might also want to, maybe even imagine, a construct here. I don't think I've got, let me see if I've got, oh, I guess I do have more specifications. Well, I guess I'll wait until I finish that. So, and here I propose some specific specifications for doing your simulations here. Do the statin doses here. It's actually the same list that I had used before. Number of posterior samples, 1,000 ought to be adequate, though if you want to do more, be my guest. And then create plots showing posterior median and 90% credible intervals for the population mean LDL percent change from baseline versus dose. It might be a good exercise also to consider some other things here. For example, and this goes to the notion I was talking about tabulating values that you might want to use for inferences. So you could be fairly probabilistic about some of this. Some, of course, you can just tabulate some of these credible intervals. So that's one thing you can do. You could ask explicit questions. So imagine that atorvastatin's already on the market. Let's suppose that of course rosuvastatin's out there now, but suppose instead that this is not, this is say a new statin or other drug that would be reducing LDL. And let's say you wanted to find out, okay, well, what dose of your new agent will result in this same effect as some particular dose of atorvastatin. So let's say you want to know what dose of rosuvastatin will produce a response comparable to, say, 40 milligrams of atorvastatin, and do that rather formally. So, for example, you could actually generate from the posterior samples the distribution of the dose of rosuvastatin that produces a response equivalent to the atorvastatin 40 milligrams. So that's one approach. Another way you can look at it is you could ask for any given dose, what's the probability that the effect exceeds atorvastatin 40 milligrams, and you could actually plot that as a function of the rosuvastatin dose. So I suggest you might want to try some explorations along those lines that takes you a bit further than just looking at the plotted credible intervals. Okay, so that's your mission, should you choose to accept it for this week. Let's step back to where we were. Let's see what's what. Jumping back too far here. Let's see. Okay, I think this is where we want. Yes. Okay. This is something that I guess when I originally did this course, I didn't do this, but it kept on coming up as a question, so ended up adding a section on it, which is how to do some of these sorts of population simulations given models that include inter-individual variation, and typically meaning these are typically models then that have been constructed by analyzing individual patient data. So they're your usual population PK and population PK/PD models. And how would I use those to generate population simulations as opposed to things like trial simulations. So I come up with a little discussion around that. So let's talk about it. So again, we're talking about simulations to describe the probable range of some population estimand, not to look at the distribution of individual patient values, but again to look at a population estimand. So suppose we want to do that, but we've got a model that's constructed by analyzing individual data. So it's usually got some inter-individual variation component. And to illustrate this and to illustrate some particular algorithms here, let's assume a model that has the following form for an observation on the ith occasion on the jth individual. So, and I'm going to use Yij to represent that. So we've got our Yij is going to be normally distributed with some expected value and a variance. And that expected value is going to be some model which is represented as a function of time, dose, drug, and other parameters in here. Of course, we could also throw in some other covariates in here, but for now we'll just focus on these. And then our parameters, at least a subset of them, may be, here we've got, notice I've got this subscripted J, so the parameters themselves may be individual specific and be distributed, in this case, according to some multivariate normal distribution. Again, for this example, I'm going to assume no intertrial variation. So now in most of the cases we're going to be doing, we're not going to have a nice closed form solution to that function for our population estimand. Typical exception to that is with models which are linear with respect to the random effects. We often can construct such an analytic solution to calculate our population estimand, but since we're usually working in the nonlinear world, that's we're not generally going to be able to do that. So we're going to use simulation instead to approximate our population estimand. And the basic notion is we're going to, excuse me, I got a buzzing phone. Do I need to answer it? No. Trying to figure out how to make it go quiet though. That ought to do it. Sorry. The basic notion here is we're going to simulate our population estimand essentially by simulating a population, or at least approximating that notion, and calculating and using some summary statistic to calculate that estimand. So what we're going to do then is we're going to use our MCMC samples again. So for each MCMC generated posterior sample for our model parameters, as well as for each set of our independent variable values, we're going to be simulating a bunch of replicates of the predicted individual responses at a particular time and treatment. So now what we're going to have is for some large number, we're probably talking typically in the thousands for each such sample. We're generating our sort of artificial population here from that. And to get our population estimand, we then use the appropriate sample statistics. So for example, to estimate our population mean, we would take a sample mean of those simulated values. If we're interested in a sample percentile, then we would use the if we're interested in a population percentile, we would use the corresponding sample percentile to estimate it. And so on. I guess another example we'd commonly encounter would be something like if you're interested in the probability of a particular event occurring, so you would simply use the fraction of the simulated events for which that occurred. So that's really the basic idea. It's brute force to simulate a population and calculate the corresponding estimand. And here I just illustrate that using a sort of a formal algorithmic form here for doing it. So here I start out, I've got an outer loop here representing our sampling from our posterior distributions. So here I'm saying, from m equals 1 to n post here. So that's some number of posterior samples we're going to work with. So first thing I'll do then is I'll sample my various model parameters from the posterior distribution. Then for that sample from our posterior distribution, I'm going to generate our pseudo population here. So that's where I'm saying for j equals 1 to n pop. So that's the number of individuals we're going to use to approximate a population. So again, that's typically going to be somewhere in the thousands, depending upon how much variability and how much sampling variability would result. Then I would do, next step would be, okay, I've got a sample from my inter-individual variability for each one of those to get an individual specific value of my parameters. I would then calculate the corresponding expected value for that individual for whatever dependent variable I'm interested in here. If there is a and then we've typically got some residual component here. I've also got a sample from that. And so I do that and I collect all of those. So I'm going to take my npop values here. And then for those npop values, I'll then calculate the appropriate sample statistic for my desired estimate. And here I just, as an example, mention the population mean, which I just use the corresponding sample mean in order to calculate that. Although I put an additional qualification here. In that special case where I'm looking at a population mean and I have a model according to the structure that I mentioned here, for that case, you actually don't need to sample from the residual variation because the expected value of this quantity is this y hat. So I could just use the y hat directly and never do this last statement there. But that isn't going to be true for all. It depends on what the estimand is. If I'm looking at a percentile, that statement would not apply. That only applies to the mean. So that's just an algorithm then to describe that process. Okay, so I'm just debating whether I wanted to say much more about that. Probably not specifically about that. So what I also want to mention is something which is used as an attempt to approximate that, and sometimes is a good approximation, sometimes not so good, but it's worth mentioning here. Is for models like these, it's often been suggested that another approach to calculating a population mean is to substitute the population mean of the parameter-specific parameters into the function for predicting a new response. And essentially what we're talking about here, I guess, is the distinction between it's much like the distinction between using it based on iPreds or Preds and non-mem. Let's see, there's a question here. Well, let me see if I can answer part of the problem I'm hesitating a little bit is if I had the posterior distribution of the quantity I want to make inferences about directly, I would do it directly. But I don't generally. Generally, what I have is posterior distributions of the parameters to work with. So that's why I have to sample from them. Now, I guess And again, I'm not sure I'm even answering your question right. I'm trying to think of a good question to try and clarify it. Uh, I mean, the first statement here is we usually do not have the posterior in a closed form that we can use to grab. And in particular, we usually don't have it for the estimand of interest. And that's the thing we want to get a posterior distribution of. And so we generally have to use simulations to get there. As I say, I'm not sure I'm answering your question, though. So if you can think of anything to clarify where you were going, let me know. Okay, back to here. So basically, the distinction I'm making here is sort of between the first case I mentioned that we use for simulating is one where we essentially simulate the equivalent of IPREDs from non-mem, although it's a little bit more complicated because we're also bringing in the uncertainty in our model parameters. Uh, in this case, in the example I'm mentioning here, it's more akin to a PRED, where you just plug in the expected value for your population of each parameter and generate and come up with a model predicted value. And here the comment I make is that I would argue that this approach would be better described, or the estimand you get out of it would be better described as the typical response for an individual, or maybe even better said, it would be the response for a typical patient rather than the mean, rather than the population mean. Uh, and again, this posterior distribution of this estimand then might be called something like the posterior distribution of a typical response. Uh, and I suppose you could argue that in and of itself may have some value, but if the thing you're really trying to compare is a population mean, it doesn't do that except in the special case where the random variables come into the equation linearly, which usually isn't going to be the case. And then I go further and I say that this distribution is not useful for informations except in cases where it's a good approximation to the distribution of the population mean response. And again, the special case there is, excuse me, models that are linear with respect to the random effects. Now, having said that, it's the one of the motivations for doing it is it's faster. So if you've got to cover a particularly large number of permutations and the cost of computation is particularly high, you may be willing to tolerate the inaccuracies associated with it. So that's anyway, just a thought on that. In addition, it's often a fairly tolerable approximation, even in the presence of some nonlinearities. And we'll actually see an example where the approximation isn't too bad. Let's see, where was I going here? Oh, this was just commenting about what one might want to do if instead of trying to describe or to make inferences about sort of central tendency, if you wanted to make inferences about inter-individual variation, how might we want to do that? And there would be different approaches we could do. Actually, I just realized there's probably a fourth one I didn't even mention here. No, I didn't actually. I'll try and remember that as I go. So I'm going to take a look at some different types of simulations that communicate somewhat different things about the distribution of individual observations. Now, one of the first ones that people often think about is to actually look at the posterior predictive distribution of individual observations. in here. So, and that's often what we do as part of our diagnostics for these models when we're trying to assess how well they fit the data, is we'll look at these posterior predictive distributions and compare them to the observed data in here. Uh, and and such so besides being useful as a model diagnostic, they are appropriate for inferences regarding the probable range of observations for that you might see in a particular individual. So if you want to make probabilistic inferences about what might happen if I were to administer that treatment to the next patient that walks in the door, then using that posterior predictive distribution is an appropriate descriptor of the probable range of outcomes that you might see. But the distribution that you get when you do that, it reflects all of our sources of variability and uncertainty in here. It reflects inter-individual variability, residual, as well as uncertainty in the model parameters. The end result is the thing you're looking at is more dispersed than I would predict for any distribution of observations in, say, a typical population. So it's not a good representation of inter-individual variability all by itself, because it reflects other sources of uncertainty in the individual observations. So if your objective is to communicate something about inter-individual variability, it's not the best way to do it. This is just, I'm not even sure it's worth going through this particular algorithm. It just describes the algorithm for doing a posterior predictive distribution given the model parameters. I suppose it doesn't hurt as a contrast to what else we're going to look at. So to get it from our posterior predictive distribution for our outcomes, what you do is for j equals 1 to however many posterior samples, you would first sample from the posterior distribution. We then sample our inter-individual our individual values of our parameters from our inter-individual variability model. We calculate our expected value based upon our model using those individual values, and then as well as throw in our random variation, and we would collect that. So there's no further summarization at that point. We just do that. So we just keep doing that over and over again here. So it's not a nested loop. It's just a single loop to generate that posterior distribution of individual observations. So that would generate a posterior predictive distribution. Now, another approach you might do, again, if you were trying to just say something about the sort of scale of inter-individual variability here, is you might want to show something I termed here the distribution of individual observations for a typical population. So the notion here is I'm going to simulate a typical distribution of observations in order to communicate the scale of variability in a typical population. Now that distribution is not suitable for any formal statistical inference, but it might be useful as kind of a communication device for, okay, this is kind of what we anticipate you would see in terms of how the observations would vary, how they would vary across a population of individuals. And this is just describing what that might look like in terms of an algorithm. We'd start out by calculating posterior means for our various parameters in here, both our fixed effects and our random effects in here. And then we would just sample a bunch of individual patients here, however many here, I say 1 to n pop, and just go ahead and generate predicted values for that. So again, this is simulating where we've basically removed our the uncertainty associated with the model parameters from the simulation. Again, that's not suitable for formal statistical inference, but it might be useful as a way to communicate the scale of variability in the observations. Here I just mentioned this is kind of a Bayesian analog to the distribution used in what's often called visual predictive checks, which are based on point estimation methods. And then the third one I was mentioning here is we could instead actually show posterior distributions, not just for our measure of central tendency in here, but we would generate posterior distributions also for tail percentiles, things like the 5th and 95th, or even the 2.5 and 97.5 percentile in our things as way of describing the variability. In fact, this is what is now come to be fairly commonly done in as part of a model diagnostic. It's a little different here because I'm talking about doing population statistics or population estimates here instead of doing them for a finite population. But it's similar to what's often done now for predictive checks, where not only do you look at the central tendency, but you also look at something in the tail, in the way of tail percentiles. So the idea here then is I'm going to do simulations to predict the posterior distribution of my tail percentiles, and that'd give you a more statistically formal way of communicating the extent of inter-individual variability. And as I say, while you're at it, you may as well simulate the population median or mean to show that. And they can all be plotted together to depict both the central tendency and variability of the observations in the population. And this is just showing you the algorithm for that. As I say here, it's essentially the same as that I described before for the population mean, except in the final step, instead of just generating the sample mean, you generate sample percentiles that include those tail percentiles. So again, you have an outer loop here, which is sampling from our posterior distribution, and an inner loop, which is sampling a artificial population here. And for each one of those simulated populations, you calculate the appropriate sample percentiles and use the distributions of those to communicate both the central tendency and the variability. And what I started hemming and hawing over a little bit earlier is, if all you wanted to do was communicate the extent of variability and not necessarily show sort of the absolute the predicted values associated with sort of the upper and lower bounds of that variability, of course you could also generate things like a sample, a population standard deviation, if you like, as another way, a standard deviation or a coefficient of variation or some such, to communicate the degree of variability. That's just the nice thing about showing the percentiles, is you're communicating both variability and scale information in one go. So it's sort of a richer representation of information about those distributions. Okay, let me take a breather again here, see if that's prompted any questions. Okay, nothing yet, but someone might still be typing. Keep an eye open. What I was going to do is illustrate a couple of the approaches with an example. Actually, was putting this together in. I've got examples of the first two cases. I haven't done the third yet here because I ran out of time here, but I can at least illustrate the basic notion here. So what I'm going to do is use an example that I stole from something I did in the MI250 course. So in that course, I had done something where we constructed, as part of the hands-on examples, we did an example involving a hypothetical factor 10A inhibitor, and we used anyway, and we looked at both the population PK and a population PD model, where we looked at a measure of factor 10A inhibition here. So we're going to use the results from that. So I'm going to use the MCMC samples from both the POP PK and PD models for this hypothetical factor 10A inhibitor. And we're going to use that to simulate posterior median and 90% credible intervals for our population mean factor 10A inhibition versus concentration. Basically, that all comes from the PD part of the model. And then we'll also simulate posterior median 90% credible intervals for population mean factor 10A inhibition versus time by dose here. So we basically got to take the dose. From that, we predict the concentrations, and from that, we predict the factor 10A inhibition in here. In the original exercise here, that was done as a sequence of two problems rather than as a single cohesive population PK/PD model, but which is probably not optimal, but it's enough to illustrate the simulation strategy. So for our example, we're going to do some single doses of placebo and a whole list here going up to 80 milligrams of our drug. For the concentration effect case, we'll do our concentration range going from 0 to 1600, and I forget the units. They were probably nanograms per mil, though I won't swear to that. Time range 0 to 24 hours, and we're going to summarize this as plots showing posterior medians and 90% credible intervals by time or concentration as appropriate for the cases I mentioned. Now let's open this up to full view. So one of the way this was originally done is when the exercise was done, is the first step was actually to do a population PK/PD model where we used the observed PK data. They were time matched with the PD outcomes, so it was just simply doing it using that rather than doing a PK model as the first step. And this was done based upon this hypothetical phase 1 single dose study in healthy volunteers. It was a parallel dose escalation design with 8 subjects per dose and a range. Whoops. Sorry, didn't mean to go right through them. Anyway, a range of doses here. PK was just plasma concentrations of parent drug, and we have a biomarker, which was an ex vivo inhibition of factor 10A activity in plasma. And you can see the various times at which that both were measured at. So the modeling objective then was just to apply a direct action PK/PD model to those time matched factor 10A and ME2 plasma concentrations. Just to give you some idea what the data had looked like here. So we've got the PK data on the left and the PD data on the right, both expressed as functions of time. This is now showing the PD data as a function of plasma concentration. So basically the exercise was essentially just to construct a model describing, that the concentration effect relationship was the PD component. And it was just a sigmoid, very simple sigmoid Emax model with, what do we got? We've got one random effect, namely in the EC50 is log normally distributed inter-individual random effect. Then the population PK exercise was one where data was combined from a that same phase 1 single dose study plus a phase 1 multiple dose and a phase 2A study here. This is just showing the information about the phase 1 multiple dose study. It was another dose escalation design here over a somewhat smaller number of doses with PK measured, essentially dense samples at the first and last dosing intervals. And then, sorry, I'm jumping all around. There we go. In a phase 2 design, which was just a one particular dose of our drug versus an active control, enoxaparin here, and it was just a parallel design here comparing those, and as part of it there was some sparse PK samples done. And this is just, again, our phase 1 single dose data there. This is our multiple dose data, and this is from the phase 2 trial where we had some sparse sampling. So from those, and the PK model was just a pretty straight ahead. Which one have we got? We've got just pretty straight ahead 2-compartment model for that. So we're not gonna do that exercise. We'll assume that exercise has been done. This has been fit to the data. It adequately describes the data. Blah blah. Okay. And what we're gonna do is take advantage of that to do some simulations consistent with at least the first 2 cases we talked about, which is to do our population means using the algorithm I showed, and then do the simulation of sort of the posterior distribution of the response in a typical patient. So that was the part of the code I distributed today. Let's see. Let's move this out of the way for now. Oops, wrong button. Yeah, let's clean up our act a little here. Okay, so let's go and get, actually, let's get rid of this for now. This is the one I distributed under the name Factor 10A Sim. And let's pull up the script here. And let's just point out what I did is these 2 files here, which I also distributed in the zip file I sent out. Those are the bugs fit objects that came from the 2 previous fitting exercise, one being doing the PK/PD model, just using the observed PK values, and then the other one being the PK model. And the idea is we'll combine those 2 to predict the probable range of population mean factor 10A inhibition values. So, and these are actually the results, those plots. So I'll show those once we get there. Okay, so as I say, this is, well, I see it marked here. It's the simulating with models that include inter-individual variation. So let's see, how much do I want to tell you? You've seen this before about the multi-process thing. You can run it with or without. In the case of the things I do for one of them, it is quite helpful because it takes a little longer. Otherwise, it takes a meaningful number of minutes, shall we say, to run. So it is useful in this case. So I put together a few functions here for simulating various quantities. This first one right here, FXA mean sim, simulates the factor 10A inhibition for a simulated population. Actually, I should say it's the mean factor 10A inhibition for a population of individuals given a particular concentration. So it would be used to answer a question like, okay, if you were to achieve a particular concentration in this individual, what would you predict the factor 10A inhibition in that patient to be at that? So it does not include the additional variability in concentration you would expect from a particular dose. So this is just looking at the uncertainty in the concentration effect response, if you like. And so you can see, and it's basically, it passes in a single row from our posterior matrix. You pass in concentration value, and this NSIM is the number of patients you're going to simulate in order to approximate a population and calculate a mean. So you can see one of the first things it does right at the outset is it generates a NSIM EC50 values from our interindividual variability of our EC50. That was our only random effect in that part of the model. And then in this sapply statement here, it's now going to step through it. This allows the user to pass in a vector of concentrations. And so it's going to calculate a population mean for each one of those concentration values. And then inside, it just generates, for a given concentration, the predicted, the factor 10A inhibition for NSIM patients, and then calculates a mean of those values. So that's pretty much the story on that. I have a similar sort of thing for our two-compartment model here. Actually, this one doesn't do a mean. This one just generates a value for any individual given parameter, vector, and the time and the dose. And then this next one is now doing something similar to that other one that was called FXA mean sim. Now it's FXA mean sim 2, but now instead of getting a population mean corresponding to a particular concentration, it calculates it for a particular dose and time in here. So by passing dose and time, it uses the PK model to calculate the concentration, which then gets passed in to calculate the predicted factor 10A inhibition. And again, the NSIM represents the number of patients that are going to be used to approximate a population in here. Let's see what else is going on. Most of this is probably old news. It does in here, again, it's generating the individual specific random effects using a multivariate normal in this instance. And this sapply plays a similar role to that last one. So this one's going to be calculating a separate population mean for each time and dose combination. And then finally, this last one that I called FXA typical sim does the same kind of thing, but instead of calculating a population mean, it calculates a sort of a prediction for a typical patient, if you like. So the idea is that first we get some measure of central tendency for each parameter, In this case, it's basically just grabbing the parameter means in here, so it never generates values from the posterior distribution. I'm sorry, it never generates values from the inter-individual variability distributions here. It just takes the point estimates and uses those directly to calculate it. Let's see a little more bookkeeping. This is just saying which parameters we're going to want to keep. The next thing's load those two files in here, which contain the corresponding. Oh, actually, I take that back from what I said earlier. I said they had the bugs fit objects. I had already pre-processed them to generate the posterior matrices, so that's what they contain. And one of them is called PD posterior, and one's called PK posterior. So when it loads those, it's going to generate those two objects in here, and then we come down and do the various simulations. Let's actually go ahead and fire up the first part of this. Just go ahead and define our various objects. That's far enough. Okay, hopefully no errors up there. Okay, good. What do we got? So the first thing I did is just generate the that concentration effect plot. And let me actually go ahead and, instead of creating the PDF documents, let me just open up a graphics window here that we can look at when we run it. Okay, so I'm specifying the concentrations I'm going to generate here, and then going ahead and running the simulations. As before, it gives you the choice of whether you want to do this parallel processing or not. I already defined multi-process as true up above. So again, this will take advantage of that. For this first simulation, it actually doesn't take very long even without it. But let's go ahead and let's make sure it's actually working right. Where the heck is that thing? Yeah, I was going to pull this up so we can actually see that it does it. You can see it. It just briefly takes advantage of the processors that are there. I think it's actually already done. I didn't do the plot yet, but yeah, it's done. So let's go ahead and a little bit of bookkeeping goes on here, and then we do the plots. Okay, so not very exciting. Also, in hindsight, I would have probably preferred a model that had a little more uncertainty in it. This was based upon some pretty rich data. And so the uncertainty bounds are actually pretty narrow, as you can see here. These are 90% credible interval. Maybe I should do more like 95s or something, so you've got a little bit more something to see. But anyway, that's what our predicted relationship here is between our population mean factor, 10A inhibition, and plasma concentration. And the next bits here, most of these start looking an awful lot alike. You'll see frequently a pattern is, I'll specify the range of independent variables I'm interested in. I will generate a design data frame or matrix that contains them, and expand grid is often a common tool to get all the possible combinations created. Oh, that's right. In this case, since I'm going to use both the PK and PD models here, I combine the two posterior matrices together. So it's not all that interesting. It's just taking the two of them and packing them together, and then doing the simulations. This one actually does take a little longer. I guess I'll go ahead and fire it up here. What time is it, by the way? Okay. When I do this one, let's pull up this guy. This one runs long enough to make the fan start going crazy on the computer, but this just also points up that, if you are working on a grid somewhere where you have the option of larger number of processors, and you have to do, a fairly large scale simulation, I certainly recommend taking advantage of it, because this kind of thing is fairly easy to do across a grid. For the example here, we could easily take advantage of, 100 nodes or something, and it would be done in a flash. Okay, maybe I shouldn't have fired that up. It does take a little bit of time. Let's see. Okay, got a question. It says WinBUGS itself can't be run on grid. Well, there actually are strategies for doing some aspects of WinBUGS. Now, within a given MCMC chain, because of the fact that each iteration depends upon the previous one, you can't run them simultaneously on on a grid. But what you can do is you can launch each chain on a separate, to a separate processor. In fact, we commonly do that to run these things a bit faster. So, and there are ways of doing it. We had actually published a few years ago a package that we called, what did I call it? It was called Bugs Parallel, for doing that. That's actually kind of obsolete now that there's some improved tools for doing parallel processing since we wrote that. What we actually do commonly in our own shop is we do most of our work now on using the using Amazon's cloud setup, and we usually use Ubuntu nodes. And in this case, and for those, we use OpenBugs, and more often than not, we'll use Sun Grid Engine for distributing the individual chains, and doing it that way. So it is something you can do. If you're doing it all within a single machine, then you can use some of the other tools. I haven't thought about doing it, but it would be possible to adapt some of the things from the parallel package in order to do exactly that too. It wouldn't be very hard. So that was a long-winded way of saying that there are things that you can do on a grid with WinBUGS, as WinBUGS, OpenBugs, JAGs. Actually, it would be particularly easy, I think, to do JAGs in conjunction with the parallel package. Okay, so it looks like it probably finished. The fan's all going down. Yeah, okay, so let's go ahead and look at the pictures. Let's do the first picture. Where'd my picture go? There it is. So here now we're looking at, let's make that a little bigger. Okay, so now we're looking at the posterior, we're looking at the posterior distributions for a population mean then for factor 10A inhibition as a function of time for various doses. So you're looking at the placebo, 1.25, 5, 10, and so on up over various doses. The different ways we could look at that. Another way I put it here just for fun is we can also do it this way where we overlay everything. The doses are distinct enough that there's not any real overlap here to see on most of these, but it's another way of viewing it. Another way I hadn't thought about, but we could also look at it. Will that work? Yeah, I think so. Let me see if I can do this without hurting myself here. If we'd rather look at this as a function of dose, and for how many time points did I do? Just trying to decide how much trouble I'm going to get into here, because there might be an awful lot of time points here. Let's see what happens. I could put time in here, and make sure I'm not going to, other than the fact I got to say dose here. I think that's all I need. Let's find out. There might be too many times here. It might be a little too tiny. I might have to weed them out. It's not as bad as it could be. So this is if you wanted to get a visualization of the dose response as a function of time in here. So you can see this is going from 0 time out to 24 hours, and you're looking at dose response at those various times. And of course, some of the dose, the change in shape is largely a reflection here of the fact that the concentrations are varying and covering a different range. What else? Oh, and the other one, this one I wanted to show you. This is looking at the posterior distribution of the response in a typical patient. Okay, let's go ahead and run it. And let's go ahead and do the first plot. Actually, I think there is only one plot. Let's go let it go ahead and run. This one doesn't take as long because, of course, you're not simulating 1,000 patients for each one of those cases. You're only simulating essentially one, so it doesn't take anywhere near as long. Okay, I think it's done already. Yeah, okay, it's done already. Now what I've done is I've overlaid. You can see I should have made those a little bigger, but the one we already did before, the mean, is in blue, and the so-called typical is in red. And what you can see here is, for all my complaints about the notion of using the typical value as being maybe not appropriate for formal inferences, at least for this particular example, they're not a lot different. They are a bit, but on the scale of the quantities we're looking at, it's not humongous. You can see, for example, here that they separate a bit as we start looking at these later times in the upper doses, but at this scale, it's not that big a difference, in spite of the fact that at least some of the random effects are coming in non-linearly. So it actually surprised me a little. I expected to see a little bigger difference, and there are models for which you may see larger differences depending upon how the random effects enter the model. Okay, and as I'd mentioned before, what I would like to do for some of these is maybe incorporate some numerical inferences as part of this. So I'll try and maybe I don't know if I'll do that for the lab session or do it for the next lecture, but I'll try and bring some of that to illustrate, how you can use some of these sorts of simulations to make some numerical statements, numerical and probabilistic statements about things like treatment comparisons. Let's see here. Let me again take a little breather, see if there's any questions. I think we're actually kind of coming to the end of the material I was going to be covering for the day. In fact, let's take a look at the slides. I think there was maybe only one little topic I was going to mention before disappearing. Okay, oh, that's right. I shoved them off to the side. There we go. Okay, well, let me go ahead and go through this. This is just, I think it's just the one slide, isn't it? Yeah. Now, up to now, I've been ignoring intertrial variation and how we would incorporate it into the simulations. And one of the reasons why is probably because I find myself in sort of maybe a somewhat ambivalent mode in terms of the role I think it should play. So in fact, I guess that's kind of what I was saying here, is that one of the reasons I haven't is because in part I still debate with myself about the best way and the most appropriate way to use intertrial variation as part of these inferences from population simulations. And it comes down in my mind to a question of what that intertrial variation represents. Of course, the answer is probably going to be somewhere in between these. But so, for example, do all of the trials randomly sample from the target population of interest, or are they sampling from a range of populations that may contain the population which is of interest to us, but not necessarily restricted to that population? And depending upon how you would answer those questions, that would influence on the role I would see intertrial variation should play in doing inferences based upon these simulations. So I say if the answer to the first question is yes, in other words, if there's just some large target population here and the patients in these trials are randomly sampling from that target population of interest, then I would calculate our population estimand by averaging over the intertrial variation. Now, actually, I should probably state that maybe even a little slightly broader. I say do all the trials randomly sample from the target population. And actually, I think what I really mean is not only would they be randomly sampling from the target population, but in some sense randomly sampling from the sort of treatment environment of interest too. So it's not only the characteristics of the patients, it's the environment the patients find themselves in. What are the concomitant therapies involved? What's the treatment environment they're in, and so on. Okay, now and then I say if the answer to the second question is yes. In other words, are we really talking about maybe a range of populations and maybe trial conditions that we're sampling from, but what we really want to make inferences about, is that we figure the case we're interested in is a subset or is a sample from those. Then if that's the case, then I would include the intertrial variation as part of the posterior distribution in our model parameters. In other words, it would contribute to the uncertainty in the model parameters in here. Now, what happens if you do that is, of course, these credible intervals will get wider if you do that, because the uncertainty, basically your posterior distribution is broader then because it includes this intertrial variation. So it means there's going to be less certainty in your inferences. Now, as I say here, to date, I tended to choose to go with the second one, in part because it's more conservative in the sense that estimated uncertainty in our population estimand is greater. But, in any given case, you may feel free to argue one or the other, depending upon what you think that intertrial variation represents and what it is you're actually interested in making inferences about. And having said that, I guess if you want to take a look, the statin gemcitabine sim case there, you notice I had a logical as part of the function here where it was intertrial equals true or false, and we did it with the false, which is equivalent to doing the first case. We're basically averaging over the intertrial variability. If you want to do it the other way, go ahead and take a look, and what you'll find is is you will see that the credible intervals are wider. In fact, I included the both results in what I distributed in the website today. So if you take a look at that, we can actually open that up here. You'll see one that says Gemcitabine with ITV, in other words, intertrial variation, and without. So if you take a look, I don't know which one of those do I want to look at here. Let's use let's use this one. So I'm going to open that and open that. So I guess you can't tell from that, but the one on the left is it's got to be without, right? Yeah, that's without. Trying to get these matched up a bit in size here. I guess they're close. So you can see that the ones on the right-hand side have broader distributions than on the left. The ones on the right include the intertrial variation as part of the posterior, whereas the ones on the left do not. So you can see any probabilistic inferences you would make would be somewhat different, even if the central tendencies are still about the same. Okay, that was pretty much all the material I had for the day. Let me see if are there any last questions or comments before we disappear. Okay, nothing popping up as I see so far. I guess I will look forward to seeing you on Monday. And just a reminder, the topic for then is where to go. Is the problem that I assigned here that we labeled as hands-on 4 here. So we'll be going over that on Monday. As I say, maybe I'll see if I can come up with some things to illustrate how you can do some of the sorts of quantitative probabilistic inferences I mentioned here as some possibilities for this case as part of it. Okay, look forward to seeing you then. Bye for now.